All right, let's get started. Let's get started. Okay, so today we'll talk primarily about the midterm. As you know, the homework deadline was moved to Monday, which is weird because I'm not going to talk about the solution on Monday. But all right, we'll do that. Monday is the midterm, of course. So in my solution, I thought I'd make one suggestion at least. So I'm writing a new solution in Rust because I need the exercise. And in my solution, I found it's easier to think about the logic of reliable transport as a sort of state diagram. So, and also implement it as a state diagram. So for your connection, you keep a state saying, oh yeah, right now I'm waiting for a SYN, let's say, or waiting for an ACK for my SYN. Right? And so all you remember is this is my state, and then you have a timeout, let's say, for your receive. And if the receive doesn't give anything back, well, then you know what state you're in. Oh, I'm in the waiting for a SYN state, so you just do that thing over again. Right? So kind of keeping it as a little state diagram with transitions between them, just a switch statement for the transition for the states, I found was helpful. You don't have to do it that way, but it kind of makes the code a little less spaghetti. Yeah?
So for testing for correctness as far as output and everything, I was following paths and you said that we might use like PNG files and we're supposed to read bytes.
Yeah. Any file should just come across with the same bytes.
So my question is how do you evaluate correct output? Like, is it just printing out whatever is coming in, or like, do you want us to?
I mean, that'll be up to Hamed, but it should be exactly the same bytes as you put in should come back out. And I think what I would do would be to compute an MD5 checksum and compare the two, like just look at the two checksums. Or like in Bash, I would do the checksum comparison, but I wouldn't compare byte by byte myself. Even with a program of my own. Yeah, MD5 is a good program for that because it'll basically, if you change one bit anywhere in the program, a good checksum like MD5 will look completely different with just one bit changed. So it's really easy to detect the difference. I would do that. Other homework questions? All right, so remember to focus on just the single packet out because with all of it at the same time, it just gets maybe too complicated. So we'll do congestion control in the next round. Yeah.
Just find in homework description that says that you restart the sender and the receiver should handle it gracefully. What does that mean?
Gracefully basically means an error message is fine. Right? But you shouldn't pretend as if this is the correct file. Right?
So if receiver receives another SYN packet, it should just print an error message and exit.
I think that would be the sanest way to handle it. It would probably also be tolerable from a user's perspective, right? It would probably also be okay if you just get the second file. But if you get half and half, that's really bad, right? So some sort of consistency should be there. And yeah, probably Hamed will look for an error message. But if you end up delivering the whole file and you say this is a reasonable use case, he's going to give you the full score with an argument at least, right? Or if he doesn't, then come and talk to me and maybe we can discuss with him together. Yeah.
Sorry, I couldn't hear the question very well. Was it asking about like what if you get like a weird SYN packet when you're already in it?
Yeah. So one of the test cases is during the transfer of a large file, or a small file on a very slow connection, who knows. During the transfer, we stop it. Like we stop the sender, kill the sender with a Control-C. And then start a new sender.
Okay.
Then what? And sort of expected behavior would be that the receiver just gives an error message, I would say. So.
Oh, so the receiver would die at that point too.
Right. Well, when you hit Control-C, there's no way to tell the receiver it should die. But when the next one comes in, the receiver can tell, oh, what's going on here? And then, gracefully quit, meaning this was problematic, not a segmentation fault or something like that. You say, I got a bad SYN or something. Yeah.
So does that mean that like if the sender gets filled midway and then this sender reconnects with another SID, that we shouldn't just assume it's like a brand new connection?
So that's what I was just discussing with Noman, that is probably also a reasonable behavior from a user's perspective. I think you should do whatever you're convinced is the right thing to do for a program that transfers a file, right? And if you're convinced, probably Ahmed can be convinced too that that's reasonable. But half and half is not reasonable for anyone, I think. Yeah.
I was going to ask about round trip time. Do you want us to, the instant the SYN or the outcome, do you want us to store that, keep it, and do we have to update it in case there's changing latencies?
Yes, if you there will be jitter in the latency. So if you get unlucky and your SYN goes the first time the SYN is 100 milliseconds, but it's in the range of the latency was maybe 110, from 100 to 120, right? So the mean is 110, and now you got unlucky and your SYN got the 100. Now you're gonna miss every one of them. And that's really no good. So you should try to kind of overestimate it and track the latency. That's the proper way to do it. And there's a standard way to do it, which we discussed in class. There's the exponentially weighted moving average, and then you add the standard deviation from that. You add TCP adds 4 times the standard deviation, which sounds generous to me, but that's good. Let's do that. Yeah.
For the round trip time in the socket, if we're doing a socket read timeout, a set read timeout, can we update it with what depending on what the RTT is first, and then before that, can we have a hard-coded read timeout first?
Right, yeah. So just like TCP, it has to kind of make up some kind of upper bound estimate of how long could it possibly take for my SYN packet to make it to the other end of the internet. And so you're fine to have that. I think TCP says 2 or 3 seconds, something like that. And then I think that a good first estimate of the mean is whatever comes back. And a good first estimate of the standard deviation is also whatever comes back. It's not 0, right? It's the entire mean. Because it's not going to go any worse than from 0 to the mean. And to double, well, I guess it could happen, right? But that's kind of unlikely. And what TCP does is, if it misses a SYN, it doubles the timeout for next time. So then you're always going to be safe. Maybe you lose 1 packet and then you kind of catch up. It would be too bad to have to get stuck in a situation where you never get it across because you had a too low estimate initially, right? So I think that's why TCP likes to double it in case conditions change over time, let's say. Yeah.
I was going to ask, when should the sender stop trying to send something to the receiver?
Yeah, that's a very good question. TCP doesn't. Generally speaking, if it gets an error message, yes, but it will continue trying to send packets forever. But it doubles the latency every time, right? So it's not a whole lot of packets.
What should we
Yeah,
do?
I think, so we have a file transfer application, right? So what we're implementing is sort of 2 things. We're implementing a reliable transfer protocol, but also a transfer application. So in the case of a file transfer application, you would probably have a timeout. Even though TCP doesn't have one, you would probably say okay, I'm not going to do this more than a couple minutes and I'm going to give up. I would say give it 5 seconds. If nothing's happening, just shut down with the timeout. That seems like an easy to grade sort of behavior. If it's running forever, I don't know. Yeah, so I would do that. That also makes it kind of nice. You kill a sender. Yeah, make it kind of long, because otherwise we can't do that other thing with half and half, right? Because the receiver will always just quit, right? Long before you get to start another sender. So make it at least 5 seconds. Yeah. All right, should we talk about midterm? Yeah. I think we should have more homeworks. right? This is great. We get some discussion when we're close to the deadline. Yeah, no, more.
Does the
Great.
receiver ever like quit by itself?
Yeah. So I think the same thing, right? It would.
Excluding like the weird syntax. Like,
Yeah. So I think the same as for the sender. If the sender doesn't see a receiver for 5 seconds, probably it'd be better to have an error message, right? Same thing on the receiver. If we have an ongoing transfer and suddenly they just stop receiving anything for quite a while, it should probably exit then, right? But don't exit like, oh, two RTTs have passed, let's exit, right? That will fix the consistency problem. You would never get like another connection coming in. But that's kind of a cheat. It doesn't solve it in general. It just kind of addresses the grading. So, okay. Let's talk about the midterm. So, the midterm is worth, what is it? 2/5 of the exam part, which is half of the total course grade. So, what is that? 20% of the total course grade, right? And the final is 30% of the total course grade. The questions are all going to be relatively long questions, right? That you have to think about an answer. It's not like, oh, what does TCP stand for? Remember this, right? It's like, oh, this thing is going on. Here's an example question that would be kind of cool. We have a connection to a TCP connection ongoing. The round trip time is 100 milliseconds. The congestion window, we're measuring the congestion window and we're seeing it's 100 packets. What's the throughput? All right. What kind of throughput are we seeing on this link? So to compute that, it's relatively easy, right? We know we have a congestion window full of packets outstanding, right? So if did I say packets? It probably should be in bytes. Much easier to compute it in bytes. So we have a 10 kilobyte congestion window. If the latency is 100 milliseconds, we can do 10 of those congestion windows per second. So it'll be 100 kilobytes per second, right? So that's maybe one example. Another one might be like, I'm sending an email from UIC to someone's Google email address, describe the path that the email travels, perhaps, and where along this path would it be possible to spy on my email, right? It's a kind of a made-up question, right? But so now you might specify like, oh, on the wireless link here, if it wasn't encrypted, and maybe like Google gets to see all the email, right? A couple of things like that would be this is not a question that would show up on the exam because it's really sloppy, but it's an example of like what it might look like, yeah.
Oh, are you posting your notes anywhere?
Yes, oh no, I forgot. I was going to attach it. Someone posted a question on Piazza. I was going to attach. I just made an RTF file of this. I was going to attach it, but then I guess I had to run to class. So, I'll do it after class. They aren't the best, but maybe they'll help some.
Is everything pretty much on there, like, testing or fair game?
I think.
Is there like a range you can give us?
Sorry. A range of what topics will be on the exam? You mean?
Yeah, because like
Yeah.
historically, I've had classes where like professors are like everything is testable, and they mean us to like literally interpret it as like memorizing dates of like when C was invented or something like that. And I'm just like,
Okay.
you said literally testable.
I see. Yeah. So I think whatever is written on here. I don't know. I don't like memorization questions, but there's a fine line between memorization and understanding, especially in systems, because you really can't memorize this stuff unless you understand it. So, but yeah, I think that these notes probably kind of define the scope relatively well, but certainly won't have all the details.
Yeah.
There's a lot that I'm talking about, and that's in a textbook that you ideally would have read. And only a few notes are on here, but I think it kind of provides us some sort of scaffolding for it. I could try to post the drawings too, but they're even worse than these, so I don't know. I'll put them on Piazza, I won't put them out in public. That said, I do make all my videos public, and I get emails from India and from all over the place, and they're asking, you removed the Git repository, where is it? I need to do the homework. That's good, it's fun. Okay, so let's see. Homework, midterm. There will be probably like 5 or 6 pages worth, a couple of little pieces on each, and most of the questions will be like that. Very little, what's it called? Multiple choice sort of answers, if any. Okay, so topics. So I think we can very broadly describe it as sort of an internet constituent parts, and then applications, and then transport layer, something like that. The next one down is network layer, and that will not be on this exam. So it'll be still necessary to understand the API of the network layer, which is like send a packet by providing a destination IP address, and it'll arrive at that site, at the other end. That's pretty much what you need to know from the network layer for this exam. Okay, so the constituent parts. It's in part we need to know about hardware, like what actually are the pieces that you make the internet out of? Cables and servers, and like what is the cloud? You say you want to store something in the cloud. What do we really mean by that? It's actually a server anywhere on the internet. It doesn't have to be in one of those fancy cloud hosting data centers. It can be in my basement too, as long as it's connected to the internet. But basically, all of the internet is either computer or cable, right? Some of those computers are routers. That's just a computer with many ports. But basically, that's all there is to it. We need to know something about the sort of layering, layers and headers, and their correspondence. So this application layer, we want to send a HTTP request to a server somewhere else. Like, what is it that we need to send to this other end, right? In order to deliver a packet to a server, to a web server, we need to send an IP packet with its destination IP address in it. We need to use a transport layer. Generally speaking, we'd use TCP for a web server. In there, we need to specify the port to connect to, port 80 for HTTP. Not so important to know that it's port 80, but I kind of would expect you to know that one. And then inside of the payload, the TCP payload, we then have the HTTP request, right, which is another header essentially. Right? So understanding sort of what the API is, what are the connections between the layers? What does one layer provide to the next layer? I think that is a very important part of the internet as a whole. Some expectations on service, right? What sort of services are provided by what layers of the internet? And what are the things that parts of the inner part of the network, right? The part that's not the edge. What does that part do? We've talked about how it's it's best effort and sort of least common denominator sort of design. But more specifically, like if I say like reliability, is that like where does that come into the picture? Which part of the internet design as a whole provides reliability? Something about sort of ownership, or let's see, the autonomous systems, like how the internet is a whole bunch of different networks connected together and basically working by agreement, by contract, rather than just by design of a single system. And I think you'll get all of these out of, I forget the chapter numbers now, but in the textbook, early on, it talks about the internet design, easy, fluffy read. Take a good look at that. I'll come back to this, probably missing parts. Yeah. Let's talk a little bit about performance estimation and expectations. Right? What can we, like, how does this thing work? There's packet drops all over the place. Where do packet drops come from? And like, how does packet drops affect performance of TCP? Of course, an important piece. There's latency. Where does latency come from? Right? Why does a packet take sometimes 100 milliseconds to deliver, sometimes 200, and sometimes it gets dropped? What's going on here? And then throughput. These are three completely independent metrics of network performance. You can have extremely high throughput, very low latency, and high packet drops, or pick any one you want. Of course, if we're using TCP, then you would always have low throughput if you had high packet drops, but that's because TCP relies on lost packets as a congestion signal. Right? But in other cases, that might not be the same. I know someone, was it? You're making a homework with more than one outstanding packet?
Sorry?
No? Okay, someone here, I forgot who it was I was talking to, was doing the current homework with more than one outstanding packet, just sending them like crazy, over and over. Who was that? No one here. Okay, maybe they're at home. And then, the latency doesn't matter, and the packet drops don't really matter either. You're extremely inefficient, but you would still get all your, you would probably get your file across eventually if you just keep blasting packets out. And so you can do that if you don't need congestion control. Okay, and then some idea of important constants. So let me see what could be some good constants. Speed of light, right? That is very important with respect to latency on the internet. In fact, speed of light, it's 300,000 kilometers per second is what I go with. Is that 200,000 miles then per second? I wouldn't use miles. Please don't use miles. Right, but in the medium that the internet usually travels through, it's not that fast because it goes through light. It goes through glass, and in glass it goes about 200,000 kilometers per second, I think, something like that. What are some other constants that are good to know? Size of the Earth, right? So I have some rough idea of where we're staying. And some yeah.
So we should be expected to know these constants prior to.
Yes. Yes.
Are you going to ask us to do like distance calculations and like the time it takes from one packet from this side of the Earth to get?
I think that you should be able to get a rough idea. Like you don't need to bring a calculator. If you want to bring a calculator, that's okay, but no cell phones. You won't need a calculator to do the math, but I want everyone to have a rough idea of the magnitude of things that matter in this class. Yeah.
You'd say we could have a piece of paper.
Piece of paper, absolutely. Yeah. So you could try to write down these two constants and see what other important constants we have. Okay, typical latencies and bandwidths of links, right? So is it nanoseconds, right? Does it take a nanosecond to go from here to there, or does it take a second to go from here to there, right? Okay, yeah, other constants. And I think I forgot to mention this, but in every class, they're not actually constants, but know your prefixes, please. Right? So, kilo, mega, giga, tera, those are good. Milli, micro, nano. We don't need to go to pico. Right? You really, really ought to know these things. If you don't know what they mean, exactly what they mean, right, then go home and study them. They're more important than everything else we talked about in class. There's a few others, but they're not as important. There's actually one that's called hecto. Have you ever heard of that? Hecto? Yeah, you would have. Anyone else who lives in the U.S., who hasn't always lived in the U.S.? What's a hecto? 100. Yeah, very good. Yeah. And there's deci. All right, that's 10. All right. Okay. Anyway, so those are really, really good to know. You've already taken 361, so you know how long it takes to read something from a disk. How long does it take to read 1 byte from a disk? An arbitrary byte anywhere on the disk. Spinning disk, like one on a hard drive.
Like directly connected to the computer?
Yeah. Anyone? Millisecond is a very good estimate. 10 milliseconds would be fine too, but a microsecond would not. Right? So millisecond, usually it's around between 5 and 10 milliseconds. That's a normal seek disk speed. This has nothing to do with the internet. But since we're here in a systems class, I might ask, would it be faster to read this thing from disk or to get it from memory in a computer next to your machine? Right? And if you don't know how long it takes to read it from disk, then that's going to be a hard question. Right? So anyway, I think it's sort of like knowing roughly how tall you are. And those things are good. You're not an inch, let's say. Okay. Let's move on. Application protocols. We're certainly going to have to know things about HTTP, not HTML, right? That's a different class. We want to know something about, okay, let's call it like this instead. World Wide Web. How does it fit together, right? Servers and pictures coming from other servers could be maybe useful to kind of understand how that fits together, but not really much HTML. Email. So here, primarily, we're interested in HTTP, maybe some DNS there. For email, what are these things? Incoming, outgoing email servers, SMTP, IMAP, POP, although that's getting a little bit outdated now, but it's still in place. And some people are using POP. POP is an alternative to IMAP. It's basically to get your emails from a receiving email server. So what's the purpose of the outgoing, the incoming email server? How does the email travel between machines? Where is it safe? And where is it sort of easy for others to read? And where is it authenticated? When can you trust who sent it? And that sort of thing. Can it be changed by others? Can I just go and change your emails? Right? If you know how it fits together, I can ask questions like that and it'll be easy to answer. Let's see. Yeah, DNS. We had an intricate homework on DNS, so we'd certainly want to know about what are those, actually I forget what they're called, record types. Right? The A type and the C name and the NS and maybe the PTR even. I think if we have those, we're in pretty good shape. There's the SOA as well, which I'm not going to ask about. Yeah?
I was just wondering, I can't remember what it was called. What was the thing that you used to check to see if an IP address is associated with an email domain? It's like you use it, you could validate whether or not this certain IP address is allowed to send whitehouse.gov.
Oh, I see. Yeah, yeah. So this is one of the sort of authentication mechanisms for email. It's not generally available, right? But some domains can put in, I think, what was it called, secure key, or I forgot the name now, but I think we have it up here somewhere.
I guess I'll see it then when I look.
Yeah. No, let me see if I can find it. Yeah, it should be before. SPF, that's it. Yeah. So basically, SPF is where you can drop a policy sort of annotation in your DNS records. So in addition to saying, oh, my IP address, the IP address for this domain is this, the mail server is this, oh, the sender policy is this, and it's not, they actually don't have a special record type for it. They put it in an info, like a generic kind of annotation field, I think. But basically it says, oh yeah, only these two machines are allowed to send email from this domain, or anyone in this subnet is allowed, or yeah, things like that. Okay, record types, sort of structure, meaning we need root servers, TLD, top level domain servers, right? Domain servers, and then we have like local resolver. Actually, does anyone know, how does my machine know, like how does it start? If I say ping a new domain name, like how does it know where to look, who to ask? Yeah.
It has like a preloaded list of the top level DNS.
Wrong. My machine doesn't actually do that. No, none of your machines do that. Yeah.
Context, one of those, I don't remember what they're called, but like Cloudflare has one, Google has one, the servers that talk to the DNS server, I think they're, I don't remember.
Right, okay, so that's sort of a special case of the local resolver. So, is that what you were going to answer?
I don't remember, but it was something like this, but like you send it straight to your ISP and you don't pay. Like,
Yeah, so in any local network, there will be a named server. And that server does the job that you were describing. That server is contacting all these other machines for you, and then keeps a copy. So that next time when someone on the local network needs to know where Amazon is, it already knows. And so it's kind of in charge of doing name resolution for you. It used to be for caching purposes. I don't really know why you do it anymore because it's so little bandwidth, but that's usually how it works, yeah.
When you say it's on a local level of use, does that mean the router is doing
It all depends. So at home, it's maybe unlikely these days, but not that unlikely that your Wi-Fi router has a local resolver in it. Certainly your ISP provides a DNS server, so when you get an IP address from them, and we'll see later how you automatically get an IP address with DHCP, it comes with a little announcement saying, oh yeah, and this is the DNS server you should be using. But you could just contact the root servers directly. There's nothing really wrong with that. It's just that that's not how it usually works. The local resolver, let me see. On a Unix machine, you can check in here, and it says which machine to contact, right? So in resolve.conf, and here it says, like, oh, that's the machine, and that was provided automatically when I got my IP address, when I signed on to the network. There's one more place that's pretty cool. This one. Etsy host. This is for a very local resolver, right? The operating system, when it gets a query, like do this get host by name or get host adder info, it'll first check /etc/hosts to see, do we have a copy of our own for like which address to use for a given name. So you can put something in there to if you want to change it for yourself. It doesn't change it for anyone else, but for your use. At some point I had /dot in here because I used to spend too much time just looking at this addictive website when it was popular, and I just had it rerouted to localhost. And that way, I couldn't go to Slashdot anymore, and I saved a lot of time. It's very good. You can do the same thing for Valve, let's say, and then you would save a lot of time too. Okay, moving on. That was DNS. So I think understanding something about the packet structure of a request, like what they look like, is useful. That'll be described in the textbook. You didn't see that much of it in the homework because I kind of give a very nice homework template for that one. But at least you'll have a good idea of like what it's like to resolve a name. So that's something. Oh, and then let's talk specifically, I think, about BitTorrent. Peer-to-peer protocols. So have some idea of what a peer-to-peer application is, like how it works, how do they find each other, right? Usually that's a big problem with a peer-to-peer application because they don't have fixed IP addresses. They tend to be all over the place. It's not like Microsoft. You always just look up Microsoft.com and then you know where to go. So how does peer discovery work? And like what can you expect in terms of performance from a peer-to-peer application compared to a client-server application like the World Wide Web, let's say. So BitTorrent in particular, I think is very interesting because of these swarms. And if I recall correctly, there's a nice little subsection on how BitTorrent works in the textbook, well worth reading. So this follows relatively well the textbook. So just kind of look at the kind of glance through it, and when there's stuff that seems really unfamiliar, take a closer look at that. Maybe I missed something by mistake, right? And maybe it slips into the exam anyway. Or if it doesn't slip into the exam, maybe it slips into your job interview later on, and it's better that you know it. So do take a look at like throughout the book in these chapters. All right, transport layer. We want to know about reliability. Actually, let's see. TCP versus UDP, understand the differences, right? Understand something about header structure. What is it that actually, what is the metadata that's sent with every packet? This idea of packetized, like turning this packetized transport, that's IP, into streams and how that works. So that would be sequence numbers. That's part of the header structure, very important for TCP. How do we achieve reliable transport? So basically, the main solution is this retransmissions if you lose an acknowledgement, or if you don't get an acknowledgement. And something about latency and congestion control. I think, let's see, retransmissions and X. Take a look at, so of course we have this cumulative X, but also take a look at selective X in the textbook. So TCP does support selective X. The general idea is you say, oh yeah, I have everything up to here, and then I have these 7 packets, but I'm kind of missing a few in between. Right? So that way you don't have to retransmit those 7 packets in the next round. You can send the missing 3 and then some more after that, perhaps, depending on how the congestion window works. So yeah, let's look at the congestion window. Like the principle of operation. Right? General idea is this, like we're sliding this congestion window over the data that we want to send, and we only move the back of the congestion window when we've received acknowledgement for the packets in the back. Right? We slide it up together with the packets. And what's nice about the congestion window is the fact that you can have many outstanding packets then. Right? With a congestion window 1, it's only 1 at a time, so only 1 per round trip time, because you have to wait for that acknowledgement from the server, and that takes an entire round trip time, right? So with a bigger congestion window, you can send some multiple of of the size of a packet back to back. Okay, something about fairness, right? How does TCP achieve fairness between flows? Something about maybe fairness with respect to other flows, other users, other transport protocols. Right? So TCP offers, what do we call it? It's kind of opt-in fairness, right? Or cooperative fairness. Everyone that speaks TCP are sort of expected to follow the same nice behavior of backing off, but it's not actually guaranteed. So what are the sort of implications of that? It offers per flow fairness. How does that impact when you have multiple users of a network that can vary the number of flows that each user has? That's really interesting. And what happens if you're competing with UDP traffic or any other traffic that's not TCP, or TCP traffic that isn't congestion controlled properly, right? How does that impact your flow? Okay, and then session management. Should definitely understand the operation of SYN, FIN, RST packets, also the main ones. Sort of the purpose and operation of these things. Wonder if I'm missing something about TCP. It feels like I'm missing something. Oh yeah. So what is the job of the transport layer? The main job is to provide, IP provides end-to-end host-to-host transport. The main job of the transport layer is to do application-to-application transport, because there's many applications on each host, so you're kind of multiplexing one IP address across many applications on the host. That's what the port number is for. But then you can get other nice services from it as well. One that I forgot to mention is sort of correctness. Actually, I don't know what to name it, but basically the checksum. So the checksum for TCP and UDP is a 16-bit sum of all 16-bit, like if you think of the packet as 16-bit numbers back to back, you just add them up. It actually skips a few of the bytes in the header. In the IP header in particular, it would have to skip the hop count, or the time to live. I don't know if you recall this, but in the IP header there's something called time to live. It's decremented for every hop along a path through the internet. And eventually when it reaches 0, if it hasn't gone to the destination yet, if it reaches 0, the router will send back a message saying this packet expired. That's what we use for traceroute. If you recall this thing. It's actually sending packets out with a small time to live, and then we get an error message back from all of these various routers along the way saying, oh, the packet expired, so I'm sorry, I dropped it. So since that changes every hop, you can't have that included in the checksum. Other than that, I think most of it is included. Anyway, what else does the TCP do, or the transport layer do? It can offer reliability, right? Doesn't always. It can offer congestion control, doesn't always. Right? It can offer session management and streaming, doesn't always. We don't have a good transport layer for like fixed length transmission. We have a good one for single packet, like just get it across, I don't care if it gets there, UDP. We have a good one for sequential, like stream-based communication. TCP, like you write bytes in order, they arrive in order at the other end. It's very good. But we don't have one that's made purely for like I have a transfer of this size I want to complete. I guess TCP was kind of good enough for that and kind of left it at that. I do think there should be a special transport protocol for that. It seems like it has very different characteristics. Okay, let me see. What am I missing? I have some notes from a previous year. Flow control. Okay, we have a few more minutes. Let me take questions. I'll do some scrolling.
I see you have a lot of stuff there for TCP and UDP. Is that like, is the exam gonna have like a large portion of that, or is it just because that was covered recently?
I think you can expect about a third of like internet, overall structure, applications, and transport protocol. Yeah.
Will you have us write like a code, like
No.
sockets?
It's possible you might get to read some code and comment on what's going to happen.
I have a question about the homework.
Okay.
I
Yeah.
just thought of it now. So it says we should handle it gracefully if they get interrupted and start sending the same file again. Does that mean from the start or from where it left off? So like if it dropped the if I had sent 6 packets and then stopped, would it start sending the 2nd, 7th packet again?
It's your application, so we're not going to run it with some other sender. So if I kill your application and I start it again, I think it'll start from the beginning, right?
Yeah, because like I was wondering, we could just exit in that case too, then, right? Even
Yeah.
if it's the same file. Okay.
Yeah. Just be sane. Yeah.
Is there a good way to tell? So like, for instance, if I just got the 2nd packet and one of my acts got dropped, it might send me the 1st packet again. So like,
Yeah,
so,
maybe. Let's see. If you have only one outstanding packet, you will never get the 2nd packet before you got the 1st packet, correct?
no, but I
So
could get the 1st packet again, and then
Yeah.
it's kind of making a decision. Is this 1st packet, did the 2nd get killed after the 2nd packet and then send me the 1st packet again because it got killed, or is it?
oh yeah. So this is actually what session management is for, right? The SYN packet. It's to distinguish between retransmissions and a new start.
Okay.
Right. So I think, probably a whole bunch of you are assuming that the first sequence number is going to be 1. And that kind of feels good for a while, because it's easy. But then when you get into these other things, it's much better to have a random number, especially a random 64-bit number. You're just never going to run into it again.
Yep, I
So
see.
it makes it much easier. Yeah.
So it says we're not gonna be writing out any code for the exam. Does that mean we don't have to know like the C APIs or anything for the library?
You should be well familiarized with the socket API because you might get some code to read, or just questions that say, oh, what if I call receive with these arguments? How long would it take? Let's say if you don't know what it means, then it's the problem, right? Okay, I think that's it. One more question?
Cryptography gonna be on the exam?
No crypto. Okay. I'll see you. Happy studying, and I'll see you on Monday.